什么反应？好像这一天要考解药，对吧？是吧 ？OK， 那我们原本的那个报告的那个截止日是10号，那个就因为另外一班有蛮多同学希望能够有这个比较充足的时间准备，所以我们把这个10号提到17号。但我们还是希望同学，如果这个你的报告已经完成了，你可以先寄给助教这样子。那我们可以先开始去做这个评分的动作。那我们的评分会考量一个点，就是说因为这些东西当然有一些是可以参考比如说网络这些东西没有问题。我们主要是让同学可以学习怎么把数学用出来。但是我们还是会参考一下，就是说它在原创的这个部分是多少这样子。所以这个部分我们需要一点时间去详细看每个环节这样子。几个重要时间就是下个礼拜2晚上我们要考期中考，所以下礼拜2早上我们就不上课，这个让同学这个专心准备晚上的期中考。那我们期末考就在期末考中。那原则上我们这个不算今天的话，我们大概只要2.5堂课就可以接下来这个线性代数，所以我们预计就是在剩下来的，我们还有今天不算还有3堂课，所以今天我们就是谈逆矩阵当然还有就是我们在这个行列式的部分介绍完逆矩阵那这个矩阵的空间它是比较重要的，我们就等这个期中考完以后，我们再介绍这样子。那接下来就是这3周就是报告的时间。那报告的部分，我们还在评估是因为有2班同学一起报告，所以我们还在评估说是我们一起在演习课的时段进行，还是说我们在正常课的时间进行因为如果正常课的时间进行的话，那我们就有很完整的，比如说每周有4个小时，就有12个小时，让大家充分发挥这个报告，这样子。那当然也有另外一个做法，就是那我们在演习课拿2班一起，但是这时间又变得很不够。就是这个是我们现在在评估的，所以目前的做法可能是就是等于说在2班的正常上课时间进行这样子。目前我们大概是这样，但是为了就是丰富度，或者是说2个班一起的时候，这个效果可能是更好的，所以我们也在考虑说，就是在演习课上把时间加长这样子。那这个是就是说我们在接下来的这个大概这样的规划这样子 ，OK。Okay, let's move on to the determinant operation. Okay, so if we want to handle the 4x4 matrix, we want to obtain the determinant for the 4x4 matrix, so we can use expansion with a row or in column. So you can use A0 equals to the element for the first row and the first column. And the 4 equals to the first row and the second column. Minus 1 equals to the first row and the third column. Okay. So this one will be cancelled because the term is 0. So the A12 equals to the calibration term minus 1 is the exponent 1 plus 2. 1 equals to the row number, 2 equals to column number. And the determinant will be the matrix with by removing the first row and the second column. So you will be the covector A13 would be equals to the calibration term with the exponent 1 plus 3. And the covector would be the matrix remove the first row and the third column. So we still have minus 1 here because this term is for A13. Okay. So this determinant, we need to remove the first row and the fourth column. Okay. So I think it's quite easy to get the determinant. And we can also use the other ways. By creating more zero terms. For example, we can let the third row multiply times the 4 and add it to the second row. So this then could be rewrite as so the matrix could be in the second row, we will create more zero term here. And one times 4 and okay, and this one. So we can use an operation to create more non-zero term. So we can expand with the first column. So we only need to calculate this term. So we can have the value, and this value will be equal to the result of expansion in the first row. And this method will be similar to the operation based on expansion with the first row. Okay. So it's a representative example for calculating the determinant of the matrix of Okay, so let's move on to the other examples. Okay, let's move on to this example. If you check the matrix, there are a lot of variable in the matrix. It means you don't need to you don't need to perform real operation. You just need to understand the basic idea on the questions. Okay. The first one is the matrix times a constant. So here is a 3 by 3 matrix. So the constant is that all the elements times the constant. So it would be equals to 5 to so the determinant of the A is given. So here the answer is this. The second question is a inverse matrix. We will mention this later. The definition for the inverse matrix is that the matrix A and B are square matrices, and A times B equals to identity matrix is a unit matrix like this. So we code B is the inverse matrix of A. Okay. So here we can consider like this. So similarly, if we could make the equation become the value. Okay, so matrix is a system, but the determinant is a value. So here, this one could be equals to determinant, 1 over determinant, so it equals to this. So similarly, the third question would be equals to this. So it should be 5 squared. And the issue number 4 is property for the determinant. So the transport matrix will equals to the determinant of the original matrix. So it equals to 1. So based on this, so the question number 5. The transpose of the matrix will not change the value of the determinant. So it equals to this. The value is not changed. So here, we can let the constant comes out. So similar to the equation, the question number 1. For the 3 by 3 matrix, so the constant will equals to the 3 cube. Okay, so it equals to okay. So here we would like to design an additional question similar to number 5. Let's look at the inverse matrix here in the example number 5. If the minus, the inverse matrix is like this, so how to solve this determinant. So similarly, transpose of the matrix will not change the value of the determinant. So we can have compare with the example number 5. Here, the constant could be 3 to the minus 3. So it should be like this. Okay. So all of these are relative to the operation for the determinant plot. Okay. Okay, let's move on to the new part, 10.4 in the textbook, page 508. It's relative to inverse matches and adjoint matches. As we mentioned here, for two square matches A and B, if the A matrix times B matrix equals to the identity matrix, the early matrix, and it equals to B matrix times A matrix. So here we code the B matrix equals to inverse matrix of the A matrix. So it's a definition for the inverse matrix. And there are some properties for the inverse matrix. For example, if you perform the inverse matrix the inverse of the inverse matrix equals to the original matrix. If you perform the transpose, then inverse will equals to inverse first, then transpose. If two matrices A and B, A times B, then inverse equals to B inverse times A inverse matrix. And property number 4, the matrix A plus matrix B and perform the inverse transform not equal to A inverse plus B inverse. Okay, so they are properties relative to inverse matrix. So we will demonstrate this property in some practice. Okay. So the third issue is adjoint matrix, or in some textbook, also called classic adjoint. Matrix is a deformation the definition for the adjoint matrix A equals to the cofactor then transpose. So for example, we have a matrix A Okay, so the adjoint matrix A equals to cofactor. Cofactor is composed of the cofactor and transpose. Okay, the reason why we need the adjoint matrix A because for a very unique property. If a matrix, the original matrix times the adjoint matrix, so we can see the first row times the first column. So it equals to determinant. And the first row times the second column. It equals to 0. The first row comes the third column, equals to 0. The result is based on the property we mentioned in last class. Okay, let's look at the second row. The second row has the first column. Because the element is not consistent, it's not matched with the cofactor. So it equals to 0. And the second row comes the second column. The element will be matched with the cofactor. So it equals to the determinant. Similarly, the second row comes the third column. The element is not matched with the cofactor, so it equals to 0. And the third row comes the first column, equals to 0. Third row comes the second column. So we can have these measures, and we notice that we can rewrite with a common factor. Like this. So this one is a unit matrix, right? So we can let the determinant go to the left side. So So we can have this equation. And please notice that you can compare with this. So based on the definition for inverse matrix, this term equals to inverse matrix for the A, right? So if we want to derive the inverse matrix for specific matrix A, we need to get the determinant first. Then we try to come out with the joint matrix of A. Then we can get A to the minus 1. So we can use a very easy example for a 2x2 matrix A. If we want to obtain inverse matrix, we need to derive the determinant of A first. So it's quite easy. The right, we can get we can write 1 times 4 minus 2 times 3, so it equals to minus 2. And adjoint matrix A equals to this, right? So we need to have a cofactor, and we perform the transpose. Okay, so Y is a cofactor of A 1, 1. We need to have a calibration term. Minus 1 is an exponent, the row number and the column number. And the value of the determinant will be remove the first row and the first column. So the second row, first column, cofactor of the second row and first column. So we remove the second row and the first column. And the cofactor of the first row and the second column. Here. So we need to remove the first row and the second column. Okay, so the answer is, so we just put the 4 cofactors into the adjoint matrix here. So okay. So the inverse matrix would be this. So the adjoint matrix A equals to the transpose of the matrix. So we could write that all the elements times minus 2. Okay. So it equals to that is the answer. Okay. Okay. For the 3 by 3 matrix A, if we want to derive the inverse matrix for matrix A, the first step we need to have the determinant for the matrix A. So I think the 3 by 3 is very easy. So we can derive with the positive on the right element, or I think this one is easy, or we can use the row operation to create more diverton. So we can have 1 times A11. So it equals to this. So the cofactor of the first row and the first column. So the determinant will remove the first row and then the first column. So minus 1 minus, so it should be 2. Okay. So this one equals to and the joint matrix A equals to this. Transpose. Okay. So we just need to derive the 9 cofactors. So the A11 equals to the calibration term with the exponent row number plus column number. And the determinant, we need to remove the first row and the first column. A12 derivation term, and remove the first row and the second column. A13 equals to this one is a calibration term. So we remove the first row and the third column. Okay. Similarly, okay, after calculation, the 9 cofactors, and we can have the adjoint matrix A here. We just put the cofactor into the matrix. So the adjoint matrix A is a matrix. It's not a determinant. So just that the row and the column is changed in the transpose operation. So it should be the first row will become the first column. Okay. So it equals to, and then we can put this one here. Okay. So it's a representative calculation for the inverse matrix. And I think that today we still have issue. Maybe we need around 1 minute or around 2 minutes to finish this part. And the second hour, we could let all of you to have more time to answer a question on the midterm test. So we just spend more 2 minutes to finish this part, to finish today's course. I think the calculation is easy, but we would like to highlight the meaning behind the calculation. Okay, so here we have matrix A. If we want to talk about the solution for the equation, we want to understand we want to know the solution for the equation. There are two representative cases. The first one is called zero. I try to use a different color. a zero solution. So you can imagine if inverse matrix exists. So you can let for the equation so we can let the equation times this term. So anything times 0 equals 0, right? So on the right, it should be 0. But on the left, this term could be cancelled out. So we can have the x always equal to 0. So it's called the zero solution. So in this case, the inverse matrix should be this. So if inverse matrix exists, and we understand this is inverse matrix. So it means the determinant of A not equals to 0, right? Because if the determinant A equals 0, the denominator term will be 0. So this term will not exist. So they have two cases. And there are another issues that if the A inverse matrix is not exist, it also means that the rank is relative to the number of pivots. So we will further talk about this after midterm test relative to the space in matrix. Okay, so this is the reason why we need to learn the calculation for the inverse matrix. So before we learn the space in the matrix, we need to understand this because it's relative to the rank. The rank is relative to the dimension of the space that the vectors in the matrix. So, for example, it's a matrix. You have a lot of row vectors and column vectors. The row vectors will span row space. The column vectors will span the column space. So there are a lot of space exist in the relative to the matrix A. So how can we derive the real space spanned in this matrix? We need to use Gauss elimination to have a reduced matrix, then we can clearly identify the number of effects, and we can clearly understand the dimension of the space because the effect number is very clear. Okay. So I think today we just start here, and we could have more time for all of you to ask any issue for the midterm test. Okay.